Today, on how it's made. Swords. Making them is half the battle. Pontoons. We'll see what keeps this business afloat. Grandfather clocks. At this factory, time is money. And fuses. We'll have a blow-by-blow description of the manufacturing process. For thousands of years, wars were won and lost by the sword. Swords help shape history. And although those days are gone, swords are not. Today, modern artisans craft historical replicas, and they go to the hilt to get the details just right. This reproduction of a medieval sword is ready to capture your imagination and take you back to the days of knights in shining armor. To make one, they place a piece of high-carbon steel in a fixture. Computer-guided blades carve out the basic geometry of the sword that has all the specifications of the original. Centuries ago, a blacksmith would have done this painstakingly by hand, but with this machine, the job is no sweat, and the cut is much more consistent. After about an hour of carving, they have a nicely tapered sword blank. They submerge it in hot liquid salt. It's a critical step. It softens the steel to eliminate stresses created by the carving. Next, they plunge the blade into containers of cool liquid in a process called quenching. It immediately hardens the edges of the sword, but the center cools more slowly. This allows the blade to retain flexibility, which will give the sword that springy quality. Using a belt grinder, they fine-tune the geometry of the blade and sharpen the edges. After that, it's sharp enough to slice paper to shreds. To test the blade's strength, they smite a metal barrel with it. Incredibly, it doesn't chip. They pump wax into molds to make historically accurate copies of the hilt parts, like the pommel, which is the counterweight at the end of the hilt, and the guard that separates the blade from the handle. They use the wax copies to cast the parts in metal. Then they grind and polish the cast metal pieces. They smooth away the rough edges on this sword guard and hone its profile. Grinding the pommel is a challenge because it has more curves and angles. One mistake, and the pommel could end up lopsided, which means it wouldn't be very effective as a counterweight. With the blade in a padded vise, they slide the guard onto the tang and cushion it with a piece of plastic and a metal pipe. Then they pound it into position with a sledgehammer. Next, they pummel the pommel into place. And then they top it off with a small piece of steel called a peen block. They blast it with a torch. This softens the peen so it spreads as they hammer it down. They apply epoxy to the wood grips and spread more epoxy on the handle of the sword. Then clamp the grips onto either side of it. Next, they brush black dye onto a thin piece of leather and coat the other side with glue. They wrap the glue and dye-drenched leather around the wooden handle. They bind it with cord to compress the leather wrap while it dries. They're now ready to brand the blade with the maker's insignia. Chemicals etch the mark into the steel, a millimeter deep. And now, you have a replica that's true to the medieval original. And it will take you back in time at sword point. Party barge, floating bridge, luxury raft. Some of the many functions of pontoon boats. While a pontoon's basic design hasn't changed much over the years, new marine materials have made these craft bigger, sleeker, sturdier, and faster, ensuring safe family fun on the lake. In the old days, 45-gallon steel drums kept pontoons afloat. That rudimentary technology has certainly evolved. Modern boats have custom-built floating chambers made of a special aluminum alloy. Floating chambers start off as sheets of aluminum. This rolling machine forms them into tubes. To curl the metal, the roller in the center applies pressure equivalent to the weight of 26 elephants. A worker slides each cylinder onto a track to stabilize it for welding. A pacing machine regulates the speed of the welding torch so that it connects the tube's edges evenly, producing a solid, watertight steel. This rolling machine, meanwhile, shapes aluminum sheets into tapered cylinders called nose cones. The operator manipulates hydraulic pressure and rollers to mold the aluminum into the right shape. They use a special aluminum alloy to make the chambers shockproof. Next step, turning the nose cone into a leak-proof chamber. First, the welder clamps the nose cone together to position it for welding. Then he begins to fuse the metal seams. The unique shape of this piece requires manual welding. This type of welding, called TIG welding, generates temperatures that can reach 5,000 degrees Celsius. The nose cones will sit at the bow of the boat, in front of the other floating chambers. The waffled component at the end of each chamber is called a baffle. It gives extra protection against leaks. This hydraulic press squeezes the sections together for an extra snug fit. Chambers are welded together to form floats. The number of chambers per float varies depending on the pontoon's length. These risers will hold the pontoon's floor in place. Each chamber floats on its own, so even with several punctures, the boat would stay afloat. A worker shoots compressed air into each chamber to check for leaks. He coats the welds with a soapy solution, which will bubble up in the case of an air leak. This demonstration shows that if air can get out through this tiny hole, then water can get in through it. Workers install aluminum cross members that will easily support all the weight that will be added on top. A worker uses a pneumatic torque wrench to bolt the cross members into the risers with rust-proof nuts. They construct the boat's floor from sheets of pressure-treated plywood. They drive these pop rivets through the wood, anchoring it securely to the cross members. Workers custom cut and glue down a marine carpet. Its fibers are plastic, so they won't rot. Now for some fade-resistant decals to festoon the pontoon. Rollers crimp aluminum side panels to make them stronger. Corrugated panels don't warp or wobble as much as flat ones. Using a pop rivet gun, a worker fastens the panels onto the railing. This shaping machine curves the railing in all the right places. It bends the soft, malleable metal with progressive pressure. Workers bring the assembled pieces to the platform. A mix of different screws and bolts secures everything onto the boat's floor, including the furniture. The pontoon's captain will control everything at the helm with this console. The switches for the horn, lights, music, and breakers sit at the top of the console for easy access. Extra touches bring some of the comforts of home to this craft. Wires and control cables connect the captain's console to this 50 horsepower motor. It's by no means a high-speed engine, but it gives the pontoon all the power it needs for a leisurely spin on the lake. Gravity drives a grandfather clock. When you wind up the clock, the cables wrap around a drum inside the mechanism, drawing the weights all the way up. Gravity then pulls the weights down gradually, unwinding the cables. That rotates the drum, which turns gear wheels, which move the hands of the clock. The proper term for this type of timepiece is long case clock. The nickname grandfather clock came from a popular song in the 1800s. This long-established company makes its clock cases out of quality hardwoods and veneers, such as maple and oak. To construct frames for the four sides and door, workers fit dowels into holes, then solidify the connecting parts with screws and glue. They lay each frame in this curing machine. It uses high-frequency radio waves to generate heat and dry the glue in seconds. Workers connect the four frames with screws and glue. They'll later attach the door frame with hinges. The next step is to assemble a base, again with dowels, glue, and screws. Once the glue is dry, the assembled frames go into the base. Now for some embellishment. Computer-guided routers carve elegant wood moldings that'll give this particular model a traditional flavor. Today's grandfather clocks come in styles to suit any decor, from ornate antique to modern urban chic. Workers carefully sand every single piece of wood making up the clock case. The surface must be flawlessly smooth for it to absorb color evenly. The moldings adhere with a combination of glue and nails. These long pieces of wood become curved, fluted moldings. They adorn the side of the door frame. This model also has a pair of stately columns above and below the flutes. A worker first positions them with glue, then, like the flutes, screws them securely to the frame from behind. The next step is to stain the wood, hand rubbing it in to bring out the grain. A coat of lacquer protects the wood and gives it a degree of sheen, from matte to glossy depending on the model. After installing the glass and door, it's time to install the clock's components, starting with long metal bars called chime rods, 8 to 12 of them, depending on the model. Each chime rod produces a certain note when struck. Next comes what's called the movement. This contains the weight-driven components that keep time and trigger the chime hammers to hit the chime rods on the hour, half hour, or quarter hour. This company uses only top-quality, all-brass movements imported from Germany. The chime hammers are also made of brass, but they have plastic tips. This muffles the sound of metal striking metal, so you hear only the note each rod produces. These brass pulleys hang from cables connected to the movement. The pulleys will support the clock's 3 weights. After connecting the movement to the clock dial, a worker inserts this model's last decorative detail, a wood panel to frame the dial. Then she installs the clock's second hand on a shaft in the center of a miniature dial. On the center shaft of the main dial, the hour and minute hands. Depending on the model, the aluminum hands are painted either black or gold. A decorative nut secures them. Finally, the all-important weights and pendulum. The weights are brass canisters filled with lead. Each one weighs almost 4 kilograms. The pendulum sways from side to side at an even pace. This ensures the clock keeps time consistently and accurately. It also drives the clock to chime on the hour or fraction of the hour. All you have to do for Grandfather Time is wind him up about once a week. Fuses have been around since the 19th century, and they're still part of the grid. Fuses are designed to blow whenever there's a strong power surge. This stops the flow of electricity and prevents a wiring fire. So by handling power overloads, fuses also take a big load off your mind. Choosing the right fuse depends on your current needs. To make a high-voltage fuse, this machine cuts notches in a long silver strip, which will serve as its element. The notches will help control the way the fuse blows. They melt bits of soft metal onto the strip. The bits will be the points where the fuse blows. They weld one end of the silver element to the top of a ceramic core, and then wind the element around it. This kind of high-voltage fuse will be used in electrical substations. They slide the element core into the fuse casing and bend back metal tabs. Then, using a soldering technique called brazing, they seal everything together. They take a brass washer and wind ignition wire around it. They're assembling the striker pin, the device that indicates a blown fuse and shuts down the power. They press fit the striker pin to the washer and, with the wire protruding, place it in a holding device. They add explosive powder to each striker pin. Then they plug the bottom of the pin with a rubber stopper. Then they press the striker pin into a brass capsule, which will contain the mini explosion that pushes out the pin when the fuse is blown. This test run shows how it all happens. They wrap the pin's ignition wire around an electrical post. They clamp down the pin and position the pendulum that swings to indicate the amount of force with which the pin fires. A jolt of electricity detonates the explosive. This causes the pin to protrude, signifying a blown fuse. Now they slide a metal eyelet onto the striker pin's ignition wire and then attach a wire coil to it to complete the ignition system for the striker pin. Using a snare, they pull the whole assembly into the fuse. They tie the end of the coil to the fuse's cap. And they press fit an outer cap over the inner one. They fill the fuse with a specific type of sand. It's a filler that absorbs energy from the element when the fuse blows. Automated rods tap the fuses to compact the sand inside. Next, they lubricate an outer cap for the other end of the fuse. And they press it onto the fuse. This machine spins grooves onto the cap, pinching it tightly to the fuse casing. They run a current through each one of these fuses, checking the voltage throughout to confirm that it's in good working order. They pump sealant around the rims of the caps to make them completely airtight. Finally, they affix the safety information. And they also stamp some electrical specifications onto the caps. Now, these fuses are ready to go with the electrical flow, and if there's trouble, they'll blow.